Let us start with the picture on the left. We have a sequence of functions, and we also have a limit function in red. We say that the sequence converges pointwise to the limit function f if the following happens. Take any point x0 in the domain, then evaluate every function in the sequence at that one fixed point. This gives a sequence of numbers, f1 of x0, f2 of x0, f3 of x0, and so on. If that sequence of numbers converges to f of x0, then we have pointwise convergence at that point. And if this works for every point x0 in the domain, then we say that the whole sequence converges pointwise to f. Now let us look at the picture on the right. Here we see another sequence of functions, again together with a limit function in red. This time the convergence is stronger. We say that fn converges uniformly to f if for every epsilon greater than 0, meaning for every tolerance band around the limit function. There exists some point in the sequence after which all later functions lie completely inside that band at every x in the domain. So the important difference is this: for pointwise convergence, we fix one point x0 and then look at what happens there. For uniform convergence, we control the whole function at once. From some index onward, the entire graph stays inside the epsilon band around the limit function, and we already know that uniform convergence is stronger than pointwise convergence. If fn converges uniformly, then it certainly converges pointwise. But the other direction is not true in general. Pointwise convergence alone does not guarantee uniform convergence. This stronger notion of convergence has a very useful consequence. Look again at the two examples. On the left, every function in the sequence is continuous, but the limit function is not continuous. It has a jump at x equals 1. On the right, every function in the sequence is continuous, and the limit function is continuous as well. And this is not just a coincidence. In fact, this always happens under uniform convergence. If every function fn is continuous, and if the sequence converges uniformly to a limit function f, then the limit function must also be continuous. And that is exactly the statement we are now going to prove. So let us move to the proof. The assumption is that we have a sequence of continuous functions, shown in different colors, and in red we see the limit function f. We further assume that the sequence converges uniformly to this red limit function, and our goal is to prove that f is continuous. Now remember what continuity means. To show that a function is continuous, we have to show that it is continuous at every point in its domain. So let us fix a point x0 in the domain. The value f of x0 is marked here on the graph. And now suppose somebody gives us an epsilon greater than 0. Geometrically, that means they give us an epsilon band around the value f of x0. To prove continuity at x0, we must respond by finding a delta greater than 0, such that whenever x lies within delta minus x0 to delta plus x0, the value f of x lies inside the epsilon band around f of x0. That is the usual epsilon-delta definition of continuity. Points that are close to x0 should be mapped to values that are close to f of x0. So how do we prove this? We use two ingredients. First, each function in the sequence is continuous. Second, the sequence converges uniformly to f. Let us start by using the assumed property that we have uniform convergence. Uniform convergence says that for every tolerance level we choose, eventually the whole graph of fn lies inside the tolerance band around the limit function f. In the proof, it is convenient not to use the full epsilon immediately, but only epsilon over 3. So we choose a green band of width epsilon over 3 around the limit function. Because the convergence is uniform, we know that there exists some index, and here we choose f40, such that the whole graph of f40 lies inside this green band around f, not just at one point, but everywhere. Now focus on the value of f40 at x0. That point is marked on the graph. Since f40 is one of the functions in our sequence, and every function in the sequence is assumed to be continuous, f40 is continuous at x0. So now we apply continuity, not to the limit function f, because that is what we are trying to prove, but to the function f40, which we already know is continuous. If we choose the tolerance epsilon over 3 around f40 of x0, then continuity of f40 tells us that there exists a delta region around x0, such that whenever x lies in that delta region, the value f40 of x stays within a distance epsilon over 3 of f40 of x0. That delta region is the purple band around x0, and we are now going to keep this delta fixed. Let us zoom in to see more clearly what is happening. we take a point x inside this delta region. Then we mark two values, the value f of x, shown on the red curve, and the value f40 of x, shown on the blue curve. Our goal is to estimate the difference between f of x and f of x0. Why? That is exactly the quantity we are interested in. If this distance is less than epsilon, we can conclude that the limit function f is continuous at the point x0. Now look at the following distances in the picture. First, the distance between f of x and f40 of x, shown in pink. Second, the distance between f of x0 and f40 of x0, shown in blue. Both these lines have a length of at most epsilon over 3. Why? Because remember, f40 stays everywhere within epsilon over 3 of the limit function. That came from uniform convergence. Third, the distance between f40 of x0 and f40 of x is at most epsilon over 3. Why? Because x lies inside the delta region we chose using continuity of f40. So each of these three distances is bounded by epsilon over 3. Now we put them together. We want to estimate the absolute difference between f of x0 and f of x. So we rewrite this difference again, but now we also just add 0. Of course, this is still equal, but now we write that 0 in a clever way. We subtract f40 of x0, then add f40 of x0 again, and we also subtract f40 of x and add f40 of x again. So we have not changed anything, we have only rewritten the expression in a useful form. Then we apply the triangle inequality. That tells us that the absolute difference between f of x0 and f of x is at most the sum of the absolute values of those three pieces. But each one of those three pieces is at most epsilon over 3. So altogether, the distance between f of x0 and f of x is at most epsilon over 3 plus epsilon over 3 plus epsilon over 3, which is just epsilon. And that is exactly what we needed to prove. We have shown that whenever x lies within that delta region, around x0 that we have found and fixed, then the value f of x lies within epsilon of f of x0. So the red value f of x lands inside the epsilon band around f of x0. That means exactly that f is continuous at x0. Now we zoom out again. What have we shown? We showed continuity at one point x0, but x0 was completely arbitrary. We never used anything special about its location, so the exact same argument works for every point in the domain. Therefore, the limit function f is continuous on the whole domain. So let us summarize the theorem we have just proved. If we have a sequence of functions fn such that every function fn is continuous, and if fn converges uniformly to a limit function f, then the limit function f is also continuous. This is one of the most important reasons why uniform convergence matters. Pointwise convergence is often too weak to preserve nice properties, but uniform convergence is strong enough to preserve continuity. And there is another very useful consequence of uniform convergence. If fn converges uniformly to f on the interval from a to b, then we may interchange the limit and the integral. In other words, the limit as n goes to infinity of the integral from a to b of fn of x dx is equal to the integral from a to b of the limit as n goes to infinity of fn of x. That is another powerful theorem, and we are going to look at that one in the next video.